Hello everyone. Today I will talk about curvature estimate for minimal surfaces associated with harmonic mappings having non-zero pole. So this is the outline of my talk, and the talk is based on this article, which is a joint work with Professor B. Bhaumik. Okay, so I will start with harmonic functions. A real valued function is called harmonic if it satisfies this Laplace equation, and a complex valued function is harmonic if both u and v are real valued harmonic function. Now we call f is univalent if f is injective. Also, in any simply connected domain, we can express f by this form, where both h and g are analytic function in D. The quantity omega defined by this is known as the dilatation of f, and this plays a crucial role in the theory of harmonic function. We call a harmonic function is sense preserving if its Jacobian is positive, and in this case the dilatation is analytic and has modulus less than 1. Now the CR construction is a useful technique to construct harmonic univalent mapping. So before describing this, let us define a CHD domain. So a domain in the complex plane is called CHD, that is convex in the horizontal direction if its intersection with each horizontal line is either connected or empty. Now the technique is based on this theorem proved by Cluny and Selzmann, which says that if f is a sense preserving harmonic mapping in the unit disk D, then f is univalent and its range is a CHD domain if and only if the analytic function h minus g has the same properties. Now what is exactly the CR construction? So suppose we have a conformal mapping phi whose image is a CHD domain. Then the horizontal CR of the function phi with dilatation omega is defined by the harmonic mapping f, where h and g satisfy these two differential equations. Okay, now for example, if we consider both phi and omega to be the identity mapping, then by solving these two equations, we get the harmonic mapping f. And from this theorem, we can say that f is univalent and f of D is a CHD domain. Now, suppose f is harmonic in this annular region, then we call a point Z0 to be a pole of f if this limit is infinite. In this article, Hengartner and Skobar proved that if f is a complex valued sense preserving harmonic univalent mapping which is defined outside the unit disk, and if f has a pole at infinity, then f can be expressed by this expansion, where h and g having series expansion of this form. Now coming to minimal surfaces. So we call a surface is a minimal surface if its mean curvature is 0 everywhere on that surface. A parametrization of a surface X is called isothermal if it satisfies these two conditions. Now this Wester's NFI representation theorem reveals a connection between minimal surface and harmonic univalent mapping. So it says that if a minimal graph is parametrized by isothermal parametrization, then its projection is a univalent harmonic mapping whose dilatation is the square of an analytic function. Conversely, if we have a sense preserving univalent harmonic mapping f whose dilatation is the square of an analytic function b, then these three formulas will represent an isothermal parametrization of a minimal graph whose projection is again the harmonic function f. Okay. Now suppose we have an isothermal parametrization of a minimal surface with its first fundamental form in this form, then the Gaussian curvature of this surface can be expressed by this formula. Now, if X is a minimal graph whose projection is the harmonic mapping f with dilatation omega is equal to b square for some analytic function b, then lambda, this lambda will be mod h prime plus g prime, and in this case the Gaussian curvature will take the form this. Now the question is how does the presence of a pole in the underlying harmonic mapping will affect the geometry of the corresponding minimal surfaces, especially the Gaussian curvature of that surface. So we will see this But before that, let us define some classes of harmonic mapping with pole. So let sigma HP be the class of all sense-preserving univalent harmonic mapping in the unit disk D, where H has a simple pole at some point Z is equal to P, and it has a series expansion of the form 3.1. Also, let sigma HRP be the class of all such function in the class sigma HP for which the complement of FD is a real line segment. Next, let SH not P be the class of all such function F in sigma HP that are normalized at origin by these conditions, and so the functions in this class SH not P will have a series expansion of the form 3.2. The class HR not P is the subclass that lies in the intersection of these two subclasses SH not P and sigma HRP. In one of our earlier papers, we proved that if F is a sense-preserving harmonic mapping with a simple pole in the unit disk, then F will be univalent and the complement of FD will be a CHD domain if and only if the meromorphic function H minus G has the same properties. So basically this theorem extended the method of CR construction to the case of harmonic mapping with pole. Now to prove the first main theorem, we need some lemmas as a tool. So in the first lemma, we proved that if F is in the class sigma HP with the usual expansion, then the coefficients of H and G will satisfy these inequalities. Here L is the length of F of del D. Del D is the boundary of the unit disk, that is the unit circle. And in the second lemma, we proved that if F is in the class sigma HRP, then the imaginary part of F can be expressed by the form 3.3. So now come to the first theorem. So here we proved that if F is in the class SHR not P, such that the complement of FD is a real interval, and if S is the minimal graph that lies above FD, then the Gaussian curvature of S at the point that lies exactly above the origin will satisfy the estimate this. Now the proof is based on Schwarzschild lemma and the structure of H prime minus G prime that comes from lemma 2. And after that, from the coefficient estimate that we get from lemma 1, we have a lower estimate for mod M, and this finally leads to the curvature estimate this. Now from this inequality, we can clearly see that the estimate depends upon the pole P. In this theorem also, we obtained an estimate for the Gaussian curvature, but here the domain is a CHD domain, which is a more general domain. Okay, so here we prove that if F is in the class sigma HP and F0 is equal to Q, and if F is the horizontal shear of the function phi, then if S is the minimal graph over FD, the Gaussian curvature of S at the point that lies above the point F0 will satisfy the estimate this. This inequality is sharp, and the equality attains for a particular type of deletion, which is this. The proof is based on the hypothesis of the shear construction and the Schwarz lemma, and the equality attains for the equality in the Schwarz lemma. Okay, now this theorem tells us that the local geometry of the surface is controlled by the pole as well as the domain, the projection domain of the surface. Now from the Weierstrass-Enneper representation theorem, we see that the harmonic function F and the height function T can be expressed by these formulas, and by considering this integral, we can express the coordinates of the minimal surface by these formulas. Now we will see an example for which the equality attains in the second theorem. So here we consider that the harmonic function F is horizontal shear of this function with deletion omega is equal to bz square for bz is equal to this. Then using this formulas, we obtain the coordinate of the minimal surface to be this u, v, and t. And in particular, for p is equal to half, the surface will look like this. To conclude, we studied harmonic mappings with non-zero pole and used them to construct minimal surfaces. Also, we obtained some curvature bounds and so that how the geometry of the surface is controlled by the pole and the projection domain. Thank you. Thank you so much.
Thank you, Santana. Majee. If you have any questions, please go ahead.
We find these curvature estimates for maximal surfaces also.
I'm not sure, but I think yes, because the whole study is based on the Westers representation. And we have a similar type of Westers representation for maximal surface as well. So I think we can, like, the similar study is possible for maximal surfaces as well.
So you told that this is possible for maximal surfaces and other.
Yes, I'm not sure, but since the Westers representation is also there for maximal surface, so I think we can connect them to complex valued harmonic functions.
Yeah. So is it harmonic or any other type of? Can it go something other than harmonic?
Harmonic, because the condition that conformal and the conformal and minimality, like the mean curvature is 0, imply that the functions are harmonic.
So conformal and minimality is conformal,
and
then minimal is equal to harmonic. So maximal is equal to maximal if and only if equal to some other harmonic or something other.
Minimal means the vanishing of the mean curvature thing. The vanishing of the mean curvature thing and the isothermal condition will give the harmonic
No,
condition.
I was thinking about this. You have so harmonic is dxx plus dyy. So can it be dxx minus dyy?
There is a paper I have seen recently. I can, like, if you want, I can tell you later, where they have like done the similar kind of studies for like deriving the Gaussian curvature estimate in terms of harmonic mapping. There are papers.
Any other questions? If there is no further questions, once again, thank you, Rajesh.
Thank you.